E equals mc squared, Einstein's mass-energy equivalence. In 1905, a 26-year-old patent clerk in Switzerland scribbled down 5 simple characters on a piece of paper: E equals mc squared. He had no idea he'd just written the equation that would kill hundreds of thousands of people and bring humanity to the brink of extinction. Albert Einstein's mass-energy equivalence formula is deceptively simple. E is energy, m is mass, and c is the speed of light. What it means is that mass and energy are interchangeable. You can convert one into the other. And because the speed of light is massive, about 300 million meters per second, and you're squaring it, even a tiny amount of mass contains an absolutely enormous amount of energy. Let's put this in perspective. 1 kilogram of matter, about the weight of a textbook, if completely converted to energy, would release 21 megatons of explosive force. That's more than the largest nuclear bomb the United States ever tested. Einstein published this equation as part of his special theory of relativity. He was trying to understand the fundamental nature of the universe, not build weapons. But the implication was clear. If you could split atoms and convert mass directly into energy, you'd have access to unimaginable power. Fast forward to 1945. Scientists on the Manhattan Project take Einstein's equation and use it to build the atomic bomb. On August 6th, little boy is dropped on Hiroshima. The bomb weighs about 64 kilograms of uranium, but only about 0.7 grams of mass is actually converted into energy. Just 0.7 grams, less than the weight of a paperclip. That paperclip's worth of mass released 15 kilotons of explosive energy, instantly vaporizing 80,000 people and leveling an entire city. 3 days later, Nagasaki, another 70,000 dead. Einstein later called signing the letter to President Roosevelt recommending the bomb's development the one great mistake of his life. The man who gave us this elegant equation spent his final years as a pacifist, horrified by what his mathematics had enabled. Today, there are over 12,000 nuclear warheads in the world, each one a practical application of E equals mc squared. The equation didn't kill anyone directly, humans did that. But it showed us how to extract the energy locked inside atoms, and we immediately weaponized it. 5 characters, hundreds of thousands dead, millions more living under the threat of nuclear annihilation. That's the legacy of the deadliest equation ever written. The Black-Scholes equation, options pricing model. In 1973, economists Fisher Black and Myron Scholes published a mathematical formula for pricing stock options. Wall Street went absolutely insane. Finally, a scientific mathematical way to price derivatives and eliminate risk. Banks and hedge funds started using it to make massive leveraged bets, confident the math would protect them. The Black-Scholes equation is C equals S0 n of d1 minus xe raised to negative rt n of d2. Don't worry about what all those symbols mean. What matters is that this equation was supposed to tell you the fair price of financial options based on variables like stock price, time, and volatility. The problem? The equation makes assumptions about how markets behave. It assumes markets move in smooth, predictable patterns. It assumes normal distribution of returns. It assumes volatility is constant, and all of these assumptions are wrong. Real markets don't behave like smooth mathematical functions. They have crashes, panics, and black swan events, massive, unpredictable jumps that the equation couldn't account for. In 1998, a hedge fund called Long-Term Capital Management, literally run by the people who created this equation, including Myron Scholes himself, who had won the Nobel Prize for it the year before, lost $4.6 billion in 4 months. The fund had used Black-Scholes to make enormous leveraged bets, thinking the math made it safe. They were wrong. The fund's collapse was so catastrophic that the Federal Reserve had to organize a $3.6 billion bailout to prevent it from triggering a complete meltdown of the global financial system. But nobody learns the lesson. Fast forward to 2008. Banks are using descendants of the Black-Scholes model to price mortgage-backed securities and credit default swaps. They're making trillion-dollar bets based on mathematical models that assume markets are predictable and risk can be calculated. Then the housing market crashes. the models were completely wrong. The impossible happened. Banks around the world started failing. Lehman Brothers collapsed. AIG needed a $180 billion bailout. The entire global financial system came within hours of complete collapse. The 2008 financial crisis destroyed $10 trillion in wealth, caused millions of people to lose their homes, and pushed the world into the worst recession since the Great Depression. And it all traced back to over-reliance on mathematical models like Black-Scholes that promised to eliminate risk but actually concentrated it to lethal levels. Here's the scariest part. We're still using these models. Derivatives trading is now a $1 quadrillion market. Yes, quadrillion with a Q. And much of it still relies on variations of the Black-Scholes model. We're betting civilization on math formulas that have already failed catastrophically, twice. The equation didn't cause the crashes directly, but it gave traders and bankers a false sense of security. It made them believe they could mathematically eliminate risk, leading them to take bets so large that when they went wrong, they nearly destroyed the global economy. Sometimes, the deadliest equations aren't the ones that build bombs. They're the ones that build false confidence. The Navier-Stokes equations, fluid dynamics. These equations describe how fluids flow: water, air, blood, oil, anything that moves like a liquid or gas. They were developed in the 1800s by Claude Louis Navier and George Gabriel Stokes, and they're fundamental to understanding everything from weather patterns to airplane design. The equations themselves are complex partial differential equations, but the key point is this: they govern fluid motion, and getting them wrong means people die. In 1986, the Space Shuttle Challenger exploded 73 seconds after launch, killing all 7 astronauts. The cause? An O-ring seal failed because engineers miscalculated how cold temperatures would affect the fluid dynamics of the seal's material. The Navier-Stokes equations could have predicted this, but the calculations weren't done properly. In 1912, the Titanic sank and killed over 1,500 people. Why did it sink so fast after hitting the iceberg? The designers miscalculated the fluid dynamics of water flooding into the ship's compartments. They thought the watertight compartments would keep it afloat, but they didn't account for how water would flow over the tops of the compartments once enough flooded. In 2005, Hurricane Katrina killed over 1,800 people and caused $125 billion in damage. Meteorologists used the Navier-Stokes equations to predict hurricane paths and intensities. The models were wrong about Katrina's strength and trajectory, leading to inadequate evacuations and preparations. Every plane crash caused by wind shear, every dam failure, every bridge collapse in a flood, the Navier-Stokes equations are involved. When engineers get these calculations wrong, structures fail and people die. Here's the really disturbing part. We still don't fully understand these equations. They're so complex that mathematicians can't even prove solutions always exist for all conditions. It's one of the 7 Millennium Prize problems. Solve it and you win $1 million. We're designing planes, predicting weather, building dams, and engineering ships using equations we don't fully understand. We know they work most of the time, but we can't mathematically prove they'll always work. Every time you fly on a plane, the wings were designed using Navier-Stokes calculations. Every time there's a hurricane warning, it's based on Navier-Stokes predictions. We're trusting our lives to equations that might have edge cases we haven't discovered yet. So far, we've been mostly lucky, but mostly is the operative word. The Drake equation. Probability of alien contact. In 1961, astronomer Frank Drake wrote down an equation to estimate how many intelligent alien civilizations might exist in our galaxy that we could potentially communicate with. The equation is n equals r star times fp times ne times fl times fi times fc times l. Each variable represents something: rate of star formation, fraction of stars with planets, number of habitable planets per star, and so on. Plug in your estimates and you get a number for how many alien civilizations are out there. Now, you might be thinking, how is this deadly? It's just speculation about aliens. Here's why it's terrifying. Depending on what numbers you plug in, you get wildly different results. Some calculations suggest the galaxy should be teeming with millions of intelligent civilizations. Others suggest we might be completely alone. This leads to the Fermi paradox. If aliens are so common, where is everybody? Why haven't we detected any signals? Why hasn't anyone visited Earth? One possible answer is called the Great Filter, a hypothesis that there's some step in the evolution of life that's incredibly unlikely or impossible to pass. Maybe it's the jump from single-celled to multicellular life. Maybe it's the development of intelligence. Or maybe, and this is the terrifying part, it's something ahead of us. What if the Great Filter is that every civilization that reaches our level of technology destroys itself? Nuclear war, bioweapons, AI gone wrong, climate collapse? What if there's something inevitable about advanced civilizations wiping themselves out before they can colonize other planets? The Drake equation suggests that intelligent life should be common. The fact that we see no evidence of it suggests something kills civilizations before they can spread, and we might be approaching that filter right now. Some scientists argue that the solution to the Fermi paradox is that we're looking at our own future extinction. The universe is silent because every civilization that gets advanced enough to send signals also gets advanced enough to destroy itself, and they all choose destruction. The Drake equation isn't directly deadly, but it's a mathematical framework that forces us to confront a terrifying possibility. We might be doomed by our own success. The same technology that lets us reach for the stars might be the thing that kills us. And if the Great Filter is ahead of us, then the Drake equation is less a formula for finding aliens and more a countdown timer to humanity's extinction. Sleep well tonight. The Lotka-Volterra equations, predator-prey dynamics. In the 1920s, mathematicians Alfred Lotka and Vito Volterra independently developed equations to model how predator and prey populations interact. The basic idea is simple. When prey is abundant, predators thrive and multiply. When predators overhunt, prey populations crash, which then causes predators to starve. The system oscillates in cycles. These equations have been applied to everything from fish populations to disease spread to economic markets. And when they're applied to humans, the implications are horrifying. In the 1960s, ecologist Paul Ehrlich used variations of these equations to predict massive human die-offs due to overpopulation. His book, The Population Bomb, predicted that hundreds of millions would starve to death in the 1970s and 80s because human population had exceeded Earth's carrying capacity. While Ehrlich's specific predictions didn't come true, thanks to the Green Revolution and agriculture, the underlying mathematics remains valid. Any population that grows beyond its resource base faces collapse. The Easter Island civilization collapsed around 1600 AD, possibly because they deforested their entire island, destroying their resource base. Their population crossed from around 15,000 to just 2,000 to 3,000. The Lotka-Volterra equations, if they'd existed then, would have predicted this collapse with chilling accuracy. Today, we're applying these equations to predict climate collapse, fishery depletion, and resource wars. The math suggests that if human population continues growing while resources decline, we're headed for a massive population correction, a euphemism for mass death through famine, disease, and conflict. Some models predict that Earth's carrying capacity is around 10 billion people with current technology. We're at 8 billion now and still growing. The Lotka-Volterra equations suggest we're approaching an inflection point where the system will correct itself through population decline. The equations also apply to disease. When a deadly pathogen emerges, the predator, in a dense human population, the prey, the mathematics predict explosive growth, followed by a crash when either the disease runs out of hosts or the population develops immunity. COVID-19 followed these mathematical patterns almost perfectly. The virus spread exponentially, then slowed as populations gained immunity or changed behavior. Over 7 million people died, a correction in the predator-prey system. The terrifying thing about the Lotka-Volterra equations is that they're amoral. They don't care about human suffering. They just describe what happens when populations interact. And when you plug in human population data, resource consumption rates, and environmental degradation, the math suggests we're in for a rough correction. Some scientists argue we can escape this through technology, that we can expand Earth's carrying capacity indefinitely. Others argue we're already in overshoot and the collapse is inevitable. Either way, the Lotka-Volterra equations are ticking away, describing the rise and fall of populations with mathematical precision, and humans are just another population in the system. The logistic growth equation, population limits. The logistic growth equation is simpler than Lotka-Volterra, but equally deadly in its implications. dn over dt equals rn times 1 minus n over k. What this means is populations grow exponentially at first, but as they approach the environment's carrying capacity, k, growth slows and eventually stops. If a population exceeds carrying capacity, it crashes. This equation has been used to model bacteria growth, animal populations, and human civilizations. And every time a population exceeds its carrying capacity, the mathematics predict the same outcome: collapse. In 1845 to 1852, Ireland experienced the Great Famine. Its population had grown rapidly due to the introduction of the potato, reaching about 8.5 million people. When the potato blight destroyed the crop, the carrying capacity of Ireland suddenly dropped below the population. The result? Over 1 million dead from starvation and disease, and another 1 to 2 million emigrated. The population crashed by about 25%. The logistic equation would have predicted this. Ireland's population had exceeded what the land could sustainably support, and when the resource base collapsed, so did the population. In the 1990s, Rwanda's population density was among the highest in Africa. Resources were scarce, land was limited, and tensions between ethnic groups escalated. In 1994, the genocide killed 800,000 people in 100 days. While the genocide was driven by ethnic hatred and political manipulation, some researchers argue that overpopulation and resource scarcity created the underlying conditions that made such violence possible. The logistic equation suggests that when populations approach or exceed carrying capacity, conflict over scarce resources becomes more likely. It's not a justification for violence, it's a mathematical description of how resource scarcity creates pressure that can explode into conflict. Today, the logistic growth equation is being applied to global human population. Earth has a carrying capacity for humans, the number of people who can live sustainably without degrading the resource base. Nobody knows exactly what that number is, but estimates range from 2 billion to 10 billion depending on technology and consumption patterns. We're at 8 billion and still growing, while simultaneously degrading farmland, depleting aquifers, overfishing oceans, and destabilizing the climate. The logistic equation suggests we're approaching an inflection point where the system will correct itself through population decline. Some countries are already experiencing this. Japan's population is declining, so is Russia's. Many European countries would be declining without immigration. Birth rates are falling globally as women gain education and economic opportunity. But what happens in regions where population is still growing rapidly while resources are declining? The mathematics predict instability, conflict, and collapse. The logistic growth equation is deadly because it reveals a hard truth. Growth can't continue forever on a finite planet. Every population that ignores this mathematical reality faces correction, either through voluntary reduction or involuntary collapse. We're in the middle of a global experiment to see if humans can be the first species to voluntarily stabilize our population before mathematics forces the issue through mass death. So far, the results are mixed. The SIR model, disease spread equations. The SIR model divides a population into 3 groups: susceptible, infected, and recovered. Using differential equations, it predicts how a disease will spread through a population based on transmission rate and recovery rate. The basic equations are: ds over dt equals negative beta si over n, susceptible people getting infected. di over dt equals beta si over n minus gamma I, infected people spreading it, then recovering. dr over dt equals gamma I, recovered people gaining immunity. These equations can predict whether a disease will cause an epidemic, how fast it will spread, and how many people will die. Get the math wrong and you get the public health response wrong, and people die. In 1918 to 1919, the Spanish flu killed 50 to 100 million people worldwide. Public health officials didn't understand the mathematics of disease spread. They didn't implement social distancing or mask mandates quickly enough. Cities that delayed interventions by just a few days saw death rates 2 to 3 times higher. The SIR model would have told them exactly when to act, how strict measures needed to be, and when it would be safe to relax them. But they didn't have the mathematics, so they guessed, and 50 million people died. In 2020, COVID-19 emerged. We had the SIR model this time. Epidemiologists ran the equations and warned that without intervention, millions would die. Some governments listened, others didn't, arguing the models were exaggerated. The models were right. Countries that followed the mathematical predictions and implemented early, strict interventions had dramatically lower death rates. Countries that ignored the math or implemented half measures saw the predicted exponential growth in cases and deaths. Over 7 million people died from COVID-19 globally. Many of those deaths were preventable if governments had followed what the SIR model predicted. The mathematics told us exactly what would happen, but politics, economics, and human psychology got in the way. Here's what makes the SIR model truly terrifying. It predicts that a sufficiently contagious and deadly pathogen could kill a significant portion of humanity before we could develop and distribute vaccines. For example, if a disease had COVID-19's contagiousness, R0 equals approximately 3, but Ebola's lethality, 60 to 90% fatality rate, the SIR model predicts billions of deaths. The mathematics are clear. Such a disease would spread exponentially, overwhelming healthcare systems, causing social collapse, and killing most infected people before vaccines could be deployed. And such diseases are possible. The 1918 flu killed 3 to 5% of the world's population with 1918 technology. A disease with similar transmission but higher lethality could be devastating today, despite our modern medicine. The SIR model isn't just an academic exercise, it's a warning system. It tells us exactly how bad things could get and what we need to do to prevent it. The question is whether we'll listen to the mathematics or let politics and economics override the equations. During COVID-19, we saw the answer. We'll listen sometimes, but not always, and millions will die as a result. The SIR model will be relevant again. There will be another pandemic. The mathematics guarantee it. The only question is whether we'll follow the equation's guidance next time or repeat our mistakes. Chaos theory and the butterfly effect. In 1961, meteorologist Edward Lorenz discovered something that would fundamentally change how we understand the world. He was running weather simulations on an early computer, and he decided to rerun a simulation from the middle by typing in numbers from a printout. The printout showed 0.506, so that's what he typed in, but the computer stored numbers to 6 decimal places, 0.506127. That tiny difference, 0.000127, caused the simulation to produce completely different weather patterns. Lorenz wrote down 3 simple differential equations that described a simplified weather system. These equations proved mathematically that long-term weather prediction is fundamentally impossible, not difficult, impossible. No matter how powerful our computers get or how much data we collect, we cannot accurately predict weather more than about 2 weeks in advance. So why is this deadly? Because it means disasters are fundamentally unpredictable beyond a short horizon. We can't give people months of advance warning about hurricanes. We can't predict droughts years in advance. We can't forecast the weather for next summer, let alone next decade. Hurricane Katrina killed 1,800 people in 2005. The 2011 Thailand floods killed 815 people. The 2003 European heatwave killed 70,000 people. All of these disasters would have been less deadly if we could have predicted them further in advance, but chaos theory mathematically proves we cannot. It gets worse. Chaos theory applies to far more than weather. It applies to economics, ecosystems, disease spread, and social systems. Any complex system with feedback loops exhibits chaotic behavior, which means long-term prediction is impossible. The 2008 financial crisis was a chaotic system collapse. Small changes in housing prices cascaded through the financial system in unpredictable ways, leading to a global meltdown that nobody saw coming. The mathematics of chaos theory explains why all the brilliant economists and risk managers failed to predict it. The system was fundamentally unpredictable. Climate change modeling uses similar equations. We can predict general trends, the planet is warming, but we cannot predict specific regional effects decades in advance. Where will droughts occur? Which cities will be hit by hurricanes? How fast will ice sheets melt? Chaos theory says precise long-term predictions are impossible. This creates a terrible policy problem. We know climate change will cause disasters, but we can't predict exactly where and when. So how do you convince people to act when the mathematics guarantee you can't give them specific warnings? Chaos theory also applies to nuclear war scenarios. Small miscalculations or miscommunications in a crisis could cascade into full-scale nuclear war through chaotic feedback loops. The Cuban Missile Crisis in 1962 brought us within minutes of nuclear war multiple times. We survived largely through luck because the chaotic nature of the crisis made rational prediction impossible. The deadliest aspect of chaos theory is philosophical. It proves that we live in an inherently unpredictable universe. We can't calculate our way to perfect safety. We can't predict all disasters. We can't eliminate risk through better modeling. We're flying blind into the future, and the mathematics prove we always will be. All we can do is prepare for general categories of disasters without knowing specifically when or where they'll strike. Lorenz's three simple equations prove that the universe is fundamentally uncertain, and not uncertainty kills people every year. We just don't know who, where, or when until it happens. The Doomsday argument, Bayesian probability. In 1983, astrophysicist Brandon Carter proposed a mathematical argument that predicts when humanity will go extinct. It's based purely on probability theory, and the conclusion is absolutely terrifying. Here's the logic. Assume you are a randomly selected human from all humans who will ever live. If humanity has a long future ahead with trillions of people to come, then you're extremely early in human history. You're in the first 0.0001% of all humans. But if humanity is near the end, then you're randomly positioned in the middle of human history, which is statistically more likely. Using Bayesian probability, Carter calculated that there's a 95% chance that humanity will be extinct within about 9,000 years. Some versions of the argument suggest much shorter timelines, perhaps just a few centuries. Now, this isn't a physics prediction like calculating when a comet will hit the Earth. It's a statistical argument based on probability, but the mathematics are sound, and multiple philosophers and mathematicians have verified the logic. The Doomsday argument suggests that the fact you exist now in the early 21st century is actually evidence that humanity doesn't have a long future ahead. If we were going to colonize the galaxy and have trillions of descendants over millions of years, the probability that you'd happen to be born in the first 200,000 years of human existence, we've been around as a species for about that long, would be infinitesimally small. It's like buying a lottery ticket and winning the jackpot. Possible, but so unlikely that if it happens, you should suspect something else is going on. Maybe the lottery was rigged, maybe you misread the ticket, or maybe, in the humanities case, there isn't going to be a jackpot. Maybe we don't have a long future ahead. Critics argue the Doomsday argument has flaws, and many philosophers reject it, but others argue it's mathematically valid and should update our probability estimates about human extinction. Combined with observable threats, nuclear weapons, climate change, AI risk, engineered pandemics, the Doomsday argument suggests we should assign a much higher probability to near-term extinction than we intuitively do. Some calculations based on this argument suggest there's a 50% chance humanity won't survive past the year 2100. Others are more optimistic, suggesting a few thousand years, but all versions of the argument agree the probability of human extinction is much higher than most people think.
The equation isn't directly deadly, it doesn't cause anything to happen, but it's deadly in the sense that it forces us to confront an uncomfortable mathematical truth. We're probably not special, we're probably not at the dawn of a vast cosmic future, we're probably somewhere in the middle of human history, which means the end isn't as far off as we'd like to believe. And if the mathematics suggest we're likely doomed within centuries rather than millennia, maybe we should be taking existential risks a lot more seriously. The Doomsday argument is a countdown timer written in probability theory, and it's ticking much faster than we want to admit. And that's all for now. I don't know why you enjoy learning about mathematical equations that predict death, economic collapse, disease pandemics, and the extinction of humanity, but hey, at least now you know which equations to blame when things go wrong.